Greetings everybody. I'm glad to be back from my hiatus, and I'm very excited about this new video that is starting right now. So I hope you are ready to go through this video, or the calculations that I'll go through with you, and I hope we enjoy at the end of it all. So let's start by looking at Canopus temperature. So we're going to be looking at the star called Canopus. It's in the constellation of Carinae, which is at the southern hemisphere of the Earth. If you are at the southern hemisphere, you see it clearly, together with the brightest star in the night sky, which is Sirius, which was the previous episode that we looked at. I didn't go through that one with you, but this one, yeah, I'm glad to be with you today. So let's start by looking at the equations that we'll be using. The first one is, if you look at the note in blue there under that diagram, so it's just a diagram that was put there. There's nothing much to look at there in terms of our temperature. But if you look at the color, if you do more research, you find out that some observers found out that it could be white. Some say that it could be both white and blue. But usually when you look at it in the night sky, it will be white. But of course there could be other colors that are being absorbed along the way before it reaches us on Earth. So we will not look much into that. We'll look at it later on when we have time. So if we look at the notes at the bottom there, we have the law of Stefan Boltzmann, the Stefan Boltzmann law, and we can see there is that formula which is at the bottom. That's energy is equal to the Stefan Boltzmann constant, the product of the Stefan Boltzmann constant and the temperature to the power of 4. So that's what we are going to base our temperature on in terms of our calculation. So we need that formula so that we can derive other formulas. And as you can see, we have our other formula, which is the luminosity L is equal to the product of the two that we have already seen, giving us the energy of the black body. But the black body, we mean black body temperature, we'll be talking about the temperature of the body itself, without influence from other temperatures coming from other factors, external factors. We're talking about the temperature of the body itself that it produces. Like how on Earth we have global warming. So if we remove those factors that are bringing that global warming, the temperature that remains that the Earth produces itself is what we call the black body temperature. So if you look at that formula, we then add the area, the surface area of the body that we're looking at. In this case, we have that star, which is Canopus. So we are saying that the surface area of that star, of that sphere per se, just basing it on that. But we know that other factors might not make it a perfect sphere. We might have other spheroids of other types that we might have to consider in other calculations. But in this case, we're just going to treat it as a sphere. So in this case, we have that area of the sphere. That's why you find that we have that 4 pi r squared. But as you can see, like where it says, therefore T is equal to the 4th root of the luminosity over 4 pi. Of course, it says 4 pi sigma r squared, but if you take the sigma just to the side, you remain with 4 pi r squared. That 4 pi r squared is the expression for the area of a sphere, the surface area of a sphere. And then we have the sigma, which is the small letter sigma, which is the Stefan Boltzmann constant, which is written above with those units. And then we have the luminosity, which you already know, which is 10,700 times the luminosity of the sun. So the luminosity of the sun is the 3.828 times 10 to the power 26, or times 10 to the power negative 26, I think, if I'm not mistaken. No, it's times 10 to the power 26, yes. Watts. That's the luminosity of the sun. And then we have the radius of the star, that's the r, where we are saying r squared. Okay, so when we substitute the values into that formula, we then find that our temperature will be 6,856.777354 kelvins, which is approximately equal to 7,000 kelvins if we put it to the nearest 1,000. But according to Wikipedia, it's even more than that. It's more than 7,000, it's around 7,400 according to Wikipedia. So that's what we have. And then absolute zero is equal to negative 273.16 degrees Celsius. So if you look at the graph of it should be pressure against temperature, and all that extrapolation that happens, and all the conventions rather, that have been considered concerning the absolute zero, because we're looking at thermodynamic temperature here. So we need to factor in that absolute zero, the triple point of water, all those things where it is ice, water, liquid and gas at the same time, all that we need to factor in all of that. Yeah, and that's how we then get this value negative 273.16 degrees Celsius. It's just an extrapolation of a graph that brings you to that value, so we need to factor in that. It's a convention, by the way, so it's not necessarily 0.16. In some cases, some use 1.15. There's a difference between there. You can do that research on your own. It's fairly easy to understand. So then plug in the values that we need to use. So we know that we just subtract, or rather we add the positive 6,856 point blah 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 plus that absolute zero, negative 270. So when the plus and the minus mix, we find that it just becomes a negative. So we're just subtracting 273.16. And then we get our 6,583 point blah blah blah, which when we put to one decimal place, it becomes 6,583.6 degrees Celsius. I hope you have understood that one. That's to one decimal place, just for a bit of accuracy. So let's move on to look at the unit of temperature, how we get that unit. But we have covered that before. You can look at the other videos of other planets, of planets. We are now looking at stars, so I'm still thinking about planets. From my hiatus, I've just been thinking about planets. So we have stars. That's what we're going to be looking at for the next year. I think we'll probably cover stars the entire year of 2024. So let us just continue with that in mind. So we have the units of Canopus' temperature. We just remove the constants or the other values that do not have units. The coefficients, the 4 pi that we're dealing with, we have to remove it, and then we remain with the values that have units, like the luminosity, it has a unit, the Stefan Boltzmann constant is a unit, and the radius is a unit, as you can see. And then we do the cancellation of like terms and play around with the equation. As you can see with those arrows, we're just switching stuff, making sure that everything is in the right place. I won't explain much. As you can see, it's quite clear how we then come up with the K, which is kelvins. So let's move on to the next segment. Now we want to see, in the case that we have temperature, the temperature that we calculated, in the case that we have that and we don't know what the luminosity is, what do we use? What formulas do we use? Which laws do we use to come up with the luminosity? So we have that Canopus, the diagram that we had. It's not a diagram actually, it just looks like a logo, but yeah, just ignore that. It's just a design that was put there. So we have, according to the Oxford Dictionary, that luminosity refers to the intrinsic brightness of a celestial object. Basically, we're just looking at the natural brightness, what it radiates into space, just to light up what's around it, something like that. Just the radiation of the light that comes from Canopus is what we're looking at, is the luminosity, the brightness of the light, exactly that natural brightness. That's what we're looking at. And then we also have that Boltzmann law. It comes in very handy. You can try to use that formula to derive the actual formula for luminosity. Just here we are trying to deal with time as well, so we want to look into that. So we're just going to go straight into the calculation using the temperature that we calculated. We use the formula that we already know, which includes the area of the body, of that spherical body, the Canopus star. That star, it's in the spherical shape. And then we know it's 4 pi r squared, like I was saying, so now you see it clearly. And then we substitute the values into that formula, so that our L becomes that fraction, or rather it becomes 4.0959 blah 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 to times 10 to the power of 30 watts. Watts, I think most of you usually know it from power and the like. We are also using it. Yeah, that's the unit for luminosity as well. And then we divide that with the luminosity of the sun, so that we can see how many times is it brighter than the sun. Like, what's the intensity of the brightness compared to that of the sun? How how many times brighter is it compared to the sun's brightness. Or we even want to see if it is actually even brighter than the sun. So we then divide that value with 3.828 times 10 to the power of 26 watts. Like we said, that's the luminosity, so it's in watts, that's the unit. But take note, we're going to be cancelling those watts and watts to include those units, so that you can see that what we're looking for is the ratio or the coefficient, which then multiplies with the luminosity of the sun, so that you can see the actual value. Instead of writing the actual value, we just show that it is what, 10,700 times. As you can see now, the answer is approximately 10,700 by the luminosity of the sun. So that L and that subscript as a circle with that dot in the middle, that symbol represents the sun. That circle and the dot in the middle, that represents the sun. So when we say L and that circle and the dot, we're talking about the luminosity of the sun. If we have, for example, R and that circle and the dot, we are talking about the radius of the sun. So what you just do is to put the coefficient or the multiplying factor, which in this case is 10,700. So we just know it's 10,700 multiplied by the luminosity of the sun, and then we get the actual value of the luminosity of our star. I was about to say planet again, my apologies. So we are just looking for that value, but we're expressing it in terms of the luminosity of the sun. I hope you understand what is going on, so let's move on. Okay, so now we look at Canopus gravity, or rather the gravity that can be experienced on Canopus. So you find that the value that you find at the end might not be exactly what you find in other sources. Most of the information you see here was based on Wikipedia, so you find that it's a bit less than that on Wikipedia, but the process is basically the same of calculations. It's just that maybe assumptions that were taken into consideration were a bit different. That's why the values are different. So a Canopus gravity, we have that diagram. So we have a purple dot, which is right at the edge, at the left there, close to the north, and then we have that blue dot at the center. It's basically representing the center in the inner core of the star. So we have that core where that hydrogen activity is happening, that nuclear fusion is happening, which produces helium and energy. I hope you have found out about that in the previous slides that came before I started talking. So you find that that's where the blue dot is. In this case, we're looking at the radius. So that green line is basically the radius of the star. That's basically what's happening here. I think if I say that it's the radius of the sphere, you get to understand more. So we're going to use two laws to calculate this gravity. We're going to use Newton's law of universal gravitation. Quite intriguing, quite fascinating. I enjoyed this one a lot. That's the G_mm over r squared, as you can see in blue in the calculations there. That's the part that we're looking at. If you read, you'll find that it's exactly what you come out with. And then we're also going to use Newton's second law of motion, which I think you all know. It gives you F is equal to ma, where the forces are proportional, inversely proportional to the acceleration. In this case, we have acceleration due to gravity, so that's why we have that. And then we multiply with the mass. As you can see, it's mg, the other equal sign there. And why we have equated the two, we are equating the two formulas from the two laws, so that we can calculate what g is, the small letter g. So we just assume that both the forces in the two laws, the forces that are talked about in the two laws, both of those forces are equal in this case, so that you find the gravity. So what happens is the two m's, the two small letter m's that we see are the mass of the object on Canopus, or the object on the star. So they cancel out. I think you all know the rule of making g subject of formula. We need to first remove the like terms, and then we deal with those that are not the same then we plug in our values, as you can see. So we now have g is equal to capital letter G or Gm over the radius squared. That green line, the radius, yes, that's the r that we're talking about. And we'll find that it's 73.3 times the radius of the sun. The radius of Canopus is 73.3 times the radius of the sun. So I think we all know what the G and the M, the capital letter M that's left there, that is the mass of Canopus. It used to be 10 times the mass of the Sun, but I think you know the stellar evolution stuff happened and the mass decreased. And right now, Canopus is in the blue loop phase, where it's not certain how the temperature is going to go, but we are sure that probably it's going to follow the path of that path at the top, according to the diagram that you saw, which was explaining the different stages of evolution of the star. So the one at the top of the low mass, we call that path for the low mass stars. We have the low mass stars and high mass stars and intermediate mass stars. In this case, we have this one, which is the Canopus is an intermediate mass star, but if you look at the path that we are going to be using, that we assume Canopus is going through, is the one at the top, which is usually for the low mass stars. The intermediate one is a bit tricky. The energy can go anyway. It's a blue loop stage, by the way. So yeah, anything can happen. It can be a supernova or not, but we are more than 50% convinced that it's not going to go through the supernova stage. It's not a high mass star, or it's not close to a high mass star, so it's going to go the other way around. It's going to become it's going to go through the planet nebula, and then planetary nebula, and then white dwarf, and then the rest is what will happen in the future. So if you find that there's a mistake that I made in the calculation, or in other things, the other facts that I've been stating, maybe it's not really a fact, it's an opinion, or a misunderstanding, then may you just point that out in the comment section on the YouTube channel, where we are going to post this video. So let's move on to look at the calculation, and then you can see where I have gone wrong, if I have gone wrong anyway. So we substitute those values that I mentioned, and then we get that value, which is approximately equal to 0.4084 meters per second squared. So it's relatively the gravity is relatively lower than the one on the Sun, according to what we see here. And then rather not on the Sun, my apologies, I mean the one on Earth, because we're going to be basing this on the Earth's gravity, which is 9.81. We are just going to use that as the control, or as a reference point, so that we can see how we can convert this, which is in SI units. SI means the standard international units. And then we have the CGS, which is the centimeter, gram, and second system of units. That's another type of system that is used alternative to the SI units. So you can see it's in centimeters, but the standard will be in meters. The second one, it's in both cases standard, so that's not really new. And then we are going to see that our value is going to be less. Like I said, the gravity on Earth is greater than the gravity on Canopus, according to our calculation, so it's obviously going to be less. So as you can see, we then get our, in CGS, it's going to be 40.84 centimeters per second squared. That's the acceleration in terms of the centimeter, gram, and second system of units for Canopus. So we are now going to move on to convert that into log of that value, so that we can see a better way of presenting that value. Okay, so basically we just say the log G, and the log of 40.84, then we get that value, which is basically approximately equal to 1.61 in CGS. CGS, like I said, is the centimeter, gram, and second system of units. As you can see with that yellow note at the bottom there, that's to 2 decimal places, just for a bit of accuracy. But according to Wikipedia, it's around 1.70 in terms of CGS. You just need to, in terms of log G of CGS, yes, it's not just that centimeters per second squared, but the log of that. So you just need to confirm maybe where I maybe underestimated rather, and then you can assist with sharing that observation in the comment section, so that we all benefit. But that's basically how we find that value. The process is just the same. It's just with the assumptions are the ones that differ. You'll find that what people used to assume in the past, they've changed because of better equipment, better technology, better telescopes that can be able to find the different types of stars that are in the universe, and how they behave, and maybe their characteristics, their luminosity, their gravity, and the like. And also that can be determined by the different radiation, X-ray. You find that with Canopus, it's a very good emitter of X-rays, so that can be analyzed. The X-rays that come from Canopus can be analyzed using the respective equipment, and also the spectral lines and the like that we will see later on. We'll start looking at magnetic fields and how we can determine that using the spectral lines and other things like the elements that are found on that star, like hydrogen. You will find that there is a spectral line that shows the existence of hydrogen and the like. So that's what we'll be looking at. But the idea is that's how we calculate these things: the gravity, the luminosity, and the temperature. The other things you can find out as we go, but for now I think we have understood what we're supposed to understand, and I hope you have enjoyed this calculation segment. It was good to be back, and I hope we'll have more videos before the year end, but probably we're going to then continue in January, because there could be a lot of pressure because of the animations that are still being made for the Shumbafoot summit that is coming very soon. There is a couple of animations that need to be made, and I promise you it's going to be very exciting, so just stay tuned and you enjoy it as we finish this year in style and we enjoy some animations from Shumbafoot. Very creative platform, I tell you, and more is to come. More is definitely going to come. So enjoy the rest of the video, and I hope you get to share your thoughts in the comment section. And we want to appreciate those who have suggested this series that we are now starting of stars, and also those that are very interested in a lot of our content. We have a lot of videos that we have. If you enjoy them, just continue to support, and we're very grateful for your continued support. And later on, if you want to then help in many other ways, some avenues will be opened. But for now, if you can just support on YouTube, that's very fine. And we have our blogs, you can also support them on there. But that's basically the video for today. I can talk all day, but I think let's stop now. You can continue with the rest of the video, looking at the facts and other things that are aligned to this very beautiful star, this bright star, the second brightest star in the night sky. So just in the evening, maybe you can just try to go out and look at the sky and just see if you can identify this star. If you can, then well done. So let's move on with the video. Thank you very much for joining me in this calculation segment. Enjoy. Cheers.